In this video, we're going to learn about intermolecular forces, or IMFs. IMFs explain why it is that molecules stick together and don't just freely float around in the gaseous phase. They explain why solids and liquids exist. We've learned a lot about intramolecular forces like covalent bonds, and you can see them diagrammed here. We've got an O bonded to an H in water. But intermolecular forces are what make it that this water molecule and the next water molecule stick together. And if I go to this model here, I've got two water molecules and they stick together where the hydrogen of one molecule and the oxygen of another are stuck. If I were to change it and try to put the two oxygens together, they repel each other. But when I have the hydrogen and the oxygen together, they stick. And that's because of this intermolecular force. And the stronger the IMFs are, the harder it is to break them apart, the higher the boiling point, for example. But more on that in another video. All right, so let's go through the different types of IMFs. One, we've got dipole-dipole interactions, and they exist between polar molecules. So if we have, for example, HCl, HCl is very polar. We've got chlorine, an extremely electronegative element with an electronegativity of 3.0 versus hydrogen's about 2.1 or so. So there's definitely a big difference in electronegativity. And so there's a dipole moment pointing towards this chlorine, meaning that it is partially negative. So if we look at the next HCl molecule, there will be attraction between this H and this Cl, and that is a dipole-dipole interaction. The next, we have hydrogen bonding, and that's just an extreme form of a dipole-dipole interaction. It requires there to be an extremely polar bond to a hydrogen. So if we take the three most electronegative elements, F, O, or N, if any of those three elements are bonded to H, then that's a polar enough bond for there to be hydrogen bonding in among the different molecules. So water, we saw before, if we have a hydrogen of one water molecule and the oxygen of another. Also, we could have a solution of NH3 and H2O where there's hydrogen bonding as the H from the NH3 and the O from the water are attracted, or the H from the water and the N from the NH3 would also be attracted to each other. I could draw an interaction like this just as well. All right, so that's hydrogen bonding. My next question is, how is it that nonpolar substances stick together if there aren't any dipole interactions going on? And things like plastics and oils, they don't just boil very easily. Try boiling oil. It'll actually start smoking before and catch fire before it boils. Well, there's a good explanation for this, and this is called London dispersion forces. And London dispersion forces are present in all molecules, not ionic compounds, but all molecular compounds, even water. Now, they might not be the strongest intermolecular force, but they are there. And they are proportional to the size of an atom or molecule's electron cloud, and they tend to be weak among smaller molecules, but if you get to a large molecule like any oil, they can apparently be very, very strong. And how do they work? Well, let's look to this video here. We've got a neon atom. And yes, neon itself is nonpolar. If we were to just freeze a neon atom and just at any given instant in time, it might be that its 10 its 10 total electrons are not perfectly evenly distributed around the atom, as we see here, where there are more on this side than on the other side. If that's the case, this right side is partially negative, just due to there being more electrons on that side at that moment. And well, if there's another neon atom nearby, then maybe it responds to this momentary asymmetric distribution of electrons, and its electrons are repelled by the electrons on this atom, and we get a partial positive lining up with a partial negative on adjacent atoms. And it's interesting because from this point, let's just say that, okay, we start allowing things to move again, right? We paused time and saw this instantaneous dipole. Well, what if the the electrons are allowed to move again? We start the clock again. Well, maybe it is that the electrons in the atom on the right start to shift leftward. If that happens, then we kind of swap dipoles and they start to push the electrons on the atom on the left towards its left side, and we get a reversal such that now the atom on the right has its partial negative over here, and the atom on the left has its partial negative over here. So what we can see is a sort of flowing back and forth of electrons among adjacent, seemingly nonpolar atoms or molecules, and they'll flow back and forth with these instantaneous dipole moments. So that explains our last IMF, London Dispersion Forces, and that's all for this video. I hope this video has helped. Feel free to leave any questions or comments in the comments section below. Thanks for watching.